This is joint work with Sébastien Lahaie in the back over there. And it's going to be a talk on combinatorial auctions. So combinatorial auctions are mechanisms used in situations where we have package bidding, such as spectrum auctions. So think of settings where you might have a bidder who value a license in New York at $100 million, a license in New England at $50 million, but the combination at more or less, for example, 200 million instead of 150 million. There's lots of different kinds of combinatorial auctions. You might imagine a sealed bid, single shot auction if there are relatively few packages and they're known. We're interested in settings where that's not the case and where an iterative format will help price discovery. So the question then becomes, what kind of prices would we like to use? You can use single item prices, you can use bundle prices. The current state of the art is to use something called the combinatorial clock auction, which uses two stages, a ascending linear auction followed by a package bidding phase. And that raises questions about how you should tie them together and what payment rules should actually be used in the end. There's some issues around using VCG. The current approach is generally to do core prices in this case. One way to think about the work that I'm about to tell you is as an alternative to the CCA. Another way to think about it is as an alternative to the first stage of the CCA and where you could bolt on a second stage upon it. The contributions here are basically the first practical implementation of a polynomial price auction, which will enable outcomes over a wide class of valuations with or without a second stage, depending on how you want to do it. I'm going to tell you about an adaptive pricing scheme, which is going to be scalable and which will provably detect item combinations to price in order to reach a market clearing situation. And hopefully I will convince you that via an empirical evaluation that this thing reaches high efficiency and fast conversions. The way that I'm going to try to do that is by showing you that it's competitive against mechanisms like iBundle for peaked multi-minded valuations, while also at the same time being competitive against linear priced mechanisms like the clock auction first stage for quadratic valuations. There's a whole lot of related work here. Rather than spend a lot of time, I'm just going to focus on the fact that there are several components of this mechanism that have appeared earlier in other forms in literature. Important papers on subgradient auctions, polynomial prices, and in fact using adaptive pricing in a different context. Okay, so a few specifics here. This is a setting with m items and n bidders and a general valuation function, vi, that's mapping packages to real values. We have an allocation, which we're going to call y, which is a feasible assignment of m items among the n bidders. We have prices, which are mapping packages to real numbers. They may either be personalized or anonymous. Mostly I'm going to be talking about anonymous prices. We have an epsilon demand set, which are the bundles that maximize a given bidder i's utility to within epsilon, and a corresponding notion of a supply set, which are the allocations that maximize a seller's revenue. And then with this, we can define competitive equilibrium. So an allocation y lies in the bidder that simultaneously lies in the bidder's demand set and the seller's supply set. When we have that, then the combination, the pair y and p, where p is a price vector, is in competitive equilibrium, and we call p the market clearing prices. And there's this really nice proposition from Bikhchandani Dostoy that says that if yp are an epsilon competitive equilibrium, then y is an efficient allocation to within epsilon n, and we're going to use this in another slide or two. Okay, so I promised you polynomial prices. What does that actually mean? Well, polynomial prices are a situation where we have a bunch of monomials drawn from some set M, which is a subset of the overall potential set of bundles, and a set of real valued coefficients that we're going to call W, one for each such monomial. And maybe the easiest way to get intuition about this is by an example. By example. So suppose I'm trying to construct cubic prices on 3 items A, B, and C, and I'm going to give myself some x sub g indicator variables. These are going to be binary variables that are going to tell me whether a particular good G is in the bundle of interest, the bundle I'm trying to price. So for example, if I have the bundle AB, I might have, for example, 2 monomials there, XA and XB with 2 coefficients, 2 and 1. So the price of AB, when I turn on the XA and XB variables, will be 3, the sum. By contrast, if I'm trying to price AC, then this set of variables will be activated, XA, XC, and XA, XC, which have these set of coefficients. Their sum is 7, so the price of AC is 7. And if I'm trying to price the full bundle, ABC, then all of the coefficients were going to be turned on. Or all the 0, 1 variables will be turned on, and therefore all the coefficients will be activated, and the sum will add up to 9. So this is the sort of structure of the prices that we're going to be using. Okay, so how does this auction work? It's going to proceed over rounds. At each round t, we're going to quote some prices p super t. We're going to start with a price vector of 0 in the first round. There's going to be an allocation computed. This is going to be y. It's going to be the one that maximizes the revenue at those prices. We're going to ask each bidder to respond to the prices as well. They're going to supply back a bundle. They're allowed to take an epsilon discount on their component of the y allocation. This epsilon discount is going to guarantee convergence. And then if we ever reach a state where the xi and the yi, that is the allocation that the buyers and the sellers state, are identical, we're going to terminate. Otherwise, we're going to do a price update. We're going to move the prices and repeat this process, and I'll talk about how we do that price update in a minute. So this is a subgradient style method. And under straightforward bidding, it's going to converge to an epsilon competitive equilibrium, and therefore it's going to be n epsilon efficient according to the proposition I showed you a few slides ago. Okay. So this is great. We're all set. We're going to be happy, excepting for the following problem. So exact revenue maximization, as is required in the algorithm I just showed you, is possible for degree d polynomial prices. But the problem is that the IP that you need to solve has order nm to the d constraints and variables, and that scales poorly even for small d. So to the rescue comes something called packing allocations. And this basically is the idea that we're going to restrict the bidders to only win the bundles that they've been bid upon, and it's an idea that Thomas Sommerholm came up with near 20 years ago now. And if you do this, then the IP only has n constraints and mt variables and becomes much more solvable. Of course, the proposition now becomes a lot more relaxed. We're going to have an auction that only terminates within epsilon of the volume maximizing allocations among those allocations that contain the bundles bid upon. And in the paper, we show another version that operates over the full bundle space, but again, gives you a much weaker set of conditions. And ultimately, efficiency is going to become an empirical question in this space. So I'll come back to that at the end of the talk. One thing that's worth noting, though, is that as a special case, the auction is efficient with single-minded bidders. Okay, so how do I update the prices in each of these rounds? Well, we're going to do a generalization of the standard linear price update to these polynomial prices. Basically, we're going to update according to excess demand. So for any given monomial m with a current coefficient w sup t, in the current round, in the next round, we're going to quote wt plus 1 for that monomial as the previous round's wt value plus some constant times the number of demanded values that contain m minus some constant times the supply bundles that contain m. Where this constant is a step size schedule that increases sublinearly. And this is consistent with the way a lot of these kinds of auctions run. Okay, so that's how we're going to update prices when we need to update prices. The next question is, how do we figure out which monomials we should actually use? So one thing to realize is that the prices are the dual variables for the efficient allocation LP. So if we have demand allocation variables little x for every allocation on the demand side, xi, and similarly y variables on the supply side, then we can write down a math program like the one that I'm showing here. Here, again, the objective here is basically social welfare, and the supply crane is a market, and the constraint is a market clearing constraint. The catch is that we have a linear set of variables, linear between 0 and 1 instead of binary variables. That's what's going on here. And we have a constraint here for every monomial that's in the current set of monomial prices. So the dual variables of these market clearing constraints are going to be the w's of our price vector. And if we get an integer solution to this math program, then we have cleared the market. Otherwise, what we need to do is augment the set m to create a cut in this program that will move us towards an integer solution and therefore towards market clearing. So this sounds great, but there's one extra trick. There's one extra problem, which is that the boxed VI variable in the objective is actually something that we as the market maker don't know. That's the private VI value of the bidders. So we need to figure out a different objective that doesn't require that information, and that gets us to something called the restricted primal, which basically replaces that objective with things that are only available or that we have available because they come from the demand and supply queries that we've executed. So that means that we can actually write this program down and solve it, but there's one more catch, which is that there's really a lot of these y variables. And in the paper, we talk about how you can use COM generation in order to get around having to have all of those variables, but I'll defer that discussion to the paper. The bottom line is that this formulation, this restricted primal, tells us what we need to do, and there's a theorem around it. Rather than go through the theorem, I'll just cut to the chase, which is basically you run that program, and if the optimal value is less than n+1, then you know that there's a non-trivial price update to do, and you do this price updating step that I described a few slides ago. Otherwise, if the optimal value is n+1 and integer, you're done. You've found market clearing prices. You can terminate the auction. Or if it's the optimal value is n+1, but it's fractional, then your price vector is insufficient, and we need to add more monomials into the price vector in order to find market clearing prices. So how should we do that? Well, you find one of these existing constraints that has a fractional value in it. Each such fractional variable has an associated allocation, and feasible supersets of those allocations correspond to new cuts and thus new price monomials. I can pick all of them and add them, or I can use a heuristic to pick a particular one. We haven't seen empirically a lot of difference here, so what I'll show you results for is the largest constraint violation heuristic. That's how we're picking additional monomials. One thing to note is that if you fail to find such a fractional solution to add, what you've actually constructed is a proof that anonymous prices are insufficient to clear this market. And so that's something that we can take advantage of. Okay, so let me show you a little bit of empirics based around this. I'm going to benchmark this against iBundle, which is similar to the ascending proxy auction. This is a bundle-priced auction. I'm also going to use the linear clock auction. In particular, this is effectively the first phase of the CCA. And I'm going to show you something called the linear price subgradient auction, which is basically this auction, but where we restrict to linear prices and where we allow full allocation as opposed to restricting to only the bidder optimal allocations. Okay, so and I'm also going to show you two valuations domains. The first one is 3 of the CATS XOR style peaked multi-minded distributions, and the second one is a quadratic model where it is multi-minded as well, but where it's not nearly as peaked. So the first little bit of results I'd like to show you is market clearing. So in this case, iBundle clears 100% of the instances for the CATS distributions for which it was designed, but not for these quadratic valuations. The linear clock phase tends to either have undermanned or max out on rounds. The linear exact model, which is again our model but with these extra restrictions, struggles with the peaked multi-minded settings from CATS, but does quite well in quadratic. And the punchline is that the adaptive price auction that we're describing here does really well pretty much across the board with the highest mean. And it fails to clear some of the examples from the paths domain, but we know why. And that's because there are certain examples in paths that actually require personalized prices, and we opt not to switch for personalized prices. They're often not a feasible thing to implement. And therefore, we just stop the auction when we reach that case, and we'll see what that does for efficiency on the next slide. You could, of course, opt to switch for personalized prices, and that would be a different design choice. So let's look at efficiency, which is arguably what we care about the most. Again, iBundle does really well in these CATS domains for which it was designed, but because of the clearing conditions that we saw on the previous slide, it doesn't clear very well in the quadratic case, and it doesn't therefore have very high efficiency. The highest efficiency for quadratic actually comes from this linear version of the current auction, but the punchline is that the adaptive auction is a very close second best across the board and therefore has the highest kind of overall effectiveness. A quick couple comments on what's driving this, or kind of how this is working, what's happening behind the scenes here. The highest observed monomial cardinality that we see tends to be around 10. And this tells us that these price terms that are being used to drive this auction are well beyond linear, and in fact, they're well beyond quadratic. So these higher order terms are really being very effective and part of the solution for why this efficiency is being achieved. And the second thing I would say is that there's actually not that many of them. So one thing to realize is that this is the examples I've been showing you are 30 good auctions. And you're seeing in this slide a representation of how many bundles are actually being used. It's typically something around 60 or so. So there's about 30 nonlinear terms that are being added into these auctions. It's not that high, especially when you think about it by comparison. The bundle price auction, for the settings where it's working really well, has about 150 bundles. So instead of 150 bundles, you're dealing with something on the order of around 60 price monomials. And in the case where the bundle prices are not working well, you get this huge number of bundles, something over 3,000 bundles that you'd have to evaluate. So it's quite parsimonious in the amount of monomials that have to be considered. So let me conclude. The paper presents the first practical implementation of a polynomial price auction. Scaling is achieved with a provably correct adaptive pricing scheme. There's an empirical evaluation, which I've shown you some of, that shows high efficiency and fast convergence. The claim is that none of the benchmark mechanisms that we've looked at effectively clears the full range of the domains of interest, but this mechanism is competitive with the bundle price auctions like iBundle for multi-minded valuations, while at the same time being competitive with the linear price auctions like the clock auction for quadratic valuations.